So coming to the Blighs creep theory, so we have something like an hydraulic structure, say maybe a barrage or a weir, which is considered and has an impervious floor, and with the sheet piles which are on the upstream side, maybe an intermediate pile, and also a downstream pile. So here the Blighs assume that the that the water always percolates, so like this, so it may percolate like here, which is shown by an arrow mark here. So then again it may percolate like this, and then might come out here at the downstream end. So here this percolating water is what assumed by Bligh is that is known as the creep length. So here he assumed that this percolating water creeps along the base of the structure, which is in contact with the subsoil, and this length of the path that is traced by the percolating water is known as the creep length. For example, this is D1 plus D1, so and this length plus D2 plus D2, D3 and D3. So that means the total base would be plus 2 times D1 plus 2 times D2 plus 2 times D3 is the creep length. Okay. He also assumed that the head loss that takes place per unit length of the creep is that is known as the hydraulic gradient, is a constant throughout the percolating passage. For example, if H is the seepage head and total length of the creep is say L, so H by L is the hydraulic gradient, which is a constant throughout the percolating passage. So thus the loss of head is proportional to the length of the creep. And also Bligh made no distinctions between the horizontal creep as well as the vertical creep. He gave the same weightage factor for the vertical as well as for the horizontal creep. So if I consider a barrier, there is impounding water of depth h, say, which is provided with a horizontal floor length of b. So we have three vertical cutoffs, one at the upstream end, other at the intermediate section, and one more at the downstream end. So now I have shown the percolating water in the form of the arrow mark, and that this percolating water will then follow the path that I have shown in the figure. So what is the total creep length now? So total creep length will be 2 times the depth of the sheet pile, that is upstream pile, 2 times the depth of the intermediate pile, 2 times the depth of the downstream pile, plus the total width of the floor. So that will be the creep length. So now according to Bligh's theory, the hydraulic gradient or loss of head per unit length of the creep is given by, that is, if H is the seepage head, L is the total length of the creep length, so that is H by L is the hydraulic gradient, so which is given by this expression. So the reciprocal of the hydraulic gradient, that is L by H, is known as Bligh's creep coefficient. So therefore L is equal to C into H, where C is known as a Bligh's creep coefficient. So according to Bligh, the following criteria have to be satisfied to ensure safety of impervious floor against the failure. First is the safety against piping. So here the length of the creep should be sufficient so that it provides a safe hydraulic gradient according to the type of the soil. For example, if you have a coarse grained soil, then C should be around 12, and the sand mixed with the boulder or gravel, then C is around 5 to 9. So here the length of the impervious floor should be such that the exit gradient should be within the permissible gradient. So then you can prevent the hydraulic structure against the piping failure. So if the creeping water comes out at the downstream hand and has got enough exit gradient, then starts removing the soil, and that progression will go on removing the soil till a piping forms, a tunnel like structure forms below the hydraulic structure, and hence the hydraulic structure will fail. Here for this, the worst condition giving the maximum value of H should be selected such that the water is at the highest possible level and no water on the downstream side. Then safety against the uplift pressure. The ordinate of the hydraulic gradient line above the bottom of the floor represents the seepage head or the uplift pressure head at that point. So for example, if H dash is the ordinate of the hydraulic gradient line above the bottom of the floor, then uplift pressure, you know that it is specific weight into the ordinate of the hydraulic gradient line above the bottom of the floor, so W into H dash. So this uplift pressure has to be resisted by the weight of the floor. So weight of the floor is say where we have a specific weight of water into G is the specific gravity of the material into thickness. So that gives the okay the weight of the floor. So for equilibrium, you know that uplift pressure must be counterbalanced by the uplift pressure. So therefore, the uplift pressure has to be equal to the weight of the floor. Okay. So that is what, hence T can be written as, so specific weight and specific weight gets cancelled out. So T is H dash by G, where H dash is the ordinate of the hydraulic gradient line from the bottom of the floor. But here by directing the thickness to the ordinate, because here minus T, here also minus T, so we have H dash minus T is equal to T into G minus 1. So therefore H dash minus T equals, say, represented as H. So this H is taken as the ordinate to the hydraulic measure from the top of the floor. So because this H dash is always from the bottom of the floor, and that's why that this thickness is directed, and hence H will give the ordinate of the hydraulic gradient line, which is from the top of the floor. So to account for any variations, we give a factor of safety is a 4/3, so and that gives the thickness. So according to the Blighs theory, you can find out the thickness of the floor at any key points of the previous floor. So there are some limitations for the Bligh's creep theory. So because he made no distinction between the horizontal and the vertical creep, he gave the same weightage to horizontal as well as the vertical creep. This method holds good as long as horizontal distance between the cutoff, there is a horizontal distance between the pile lines is greater than their depth. And he also made no distinction between the effectiveness of the outer or inner surfaces of the sheet piles. So, but it is found that the outer faces of the end sheet piles are much more effective than the inner ones. So he made no distinction between the short and long intermediate piles. So intermediate piles of length shorter than the outer ones are generally ineffective. So that he made no distinction between the short and long intermediate piles. According to Bly, the loss of head is proportional to the creep length, but it is not true. But the actual uplift pressure distribution is not linear, but it follows a sine curve. And Bly did not specify the absolute necessity of providing a cutoff at the downstream end of the flow. So, however, it was absolutely essential to provide a deep vertical cutoff at the downstream to generally to prevent the piping. So, these were some of the limitations of the Bly's creep theory. So according to the Lane's weighted creep theory, so Lane approached the problem by making a statistical examinations of nearly 290 existing structures on previous foundation, and he evolved a theory in 1932 which is known as Lane's weighted creep theory. So he indicated that the horizontal creep is generally less effective than the in reducing the uplift than the vertical creep. Therefore, he gave a weightage factor of 1/3 for the horizontal creep, whereas he gave 1 for the vertical creep. So that's the difference. So there were different weightages for horizontal as well as for the vertical. Mm, to ensure safety for piping, so Lane suggested that the length of the creep should not be less than C1 times H, where C1 is the Lane's weighted coefficient of creep, which he gave for different type of soil. So these are some of the coefficients that are to be used, like for very fine sand or silt. So he gave the coefficient as 8.5. Similarly, for fine sand, he gave it as 7. For coarse sand, it is around 5. For gravel and sand, it is 3 to 3.5, whereas for boulders and gravel, it is 2.5 to 3, and for clay soil, 1.6 and 3. So now solving a problem on Bligh's creep coefficient. So now here a figure shows a section of a hydraulic structure which is founded on sand. So you have to calculate the average hydraulic gradient. So also find the uplift pressures at the point 6 meters from the upstream end. Similarly at 12 meters and similarly at 18 meters. And also we have to find the thicknesses at each of these at these points. So it is given there is an upstream pile of 6 meters depth and also a downstream pile of depth 8 meters. That the total length is 22 meters. The heading up of water is 2 meters. Now we can find the total length of the creep. So total length of the creep is 2 times 6 plus 22 meters plus 2 times 8. So that gives 50 meters. So the heading up of water is 2 meters. So 2 divided by total length of the creep, that is 50 meters, gives 1 in 25 as the hydraulic gradient. So now you know that we want to find the thickness at the point A. So therefore the length of the creep up to A is 2 times 6 plus 6. So that gives 18 meters. So now what is the unbalanced head at A? So that means the head lost is now 1 in 25 into 18. Okay, so that is the head lost. So therefore the unbalanced head is now H is that 2 out of 2 meters, so much gone. So 2 minus 1 in 25 into 18, that is 1.28. So now we know that the unbalanced head is 1.28. So therefore using in the formula for the thickness, that is 4 by 3 into H by G minus 1, where G is the specific gravity of the for the floor, which is taken as 2.4. So that gives 1.22 meters. So therefore the thickness of the floor at A should be 1.22 meters. Similarly, say coming to B point, so length of the creep up to is 2 times 6 plus 12, so that gives 24 meters. So therefore the unbalanced head will be so the head lost is 1 in 25, that is hydraulic gradient into the length, that is into 24, so much is the head loss. So therefore the unbalanced head is 2 minus this, so that gives 1.04. So therefore we can find the thickness of the floor here as 4 by 3 into unbalanced head is 1.04 divided by 2.4 minus 1 comes to 0.99, say 1 meter. And similarly at C we can find what is the length. So it is 2 into 6 plus 18 meters, so that gives 30 meters. So unbalanced head at C will be 2 minus 1 in 25 into 30, so that gives 0.8 meters. So therefore thickness of the floor can be around 4 by 3 into unbalanced head divided by 1.4, that gives 0.76, hence 0.8 meters is the thickness of the floor at C. So this is how you solve the problems by Bligh's theory. Now coming to the most important topic, which is known as the Khosla's theory. Here in 1926 and 27, say some siphons of Upper Janab Canal were designed on the basis of the Bligh's theory, and which faced the undermining problems. So during investigation, the actual pressure measurements were made, and these pressure measured were different from those that have been computed by Bligh's theory. So according to the investigations that have been done, so these led to the following conclusions. So which was the limitations of the Bligh's theory? Also, the outer faces of the end sheet piles were much more effective than the inner ones, and the horizontal length of the floor. So therefore the outer faces of the end sheet piles were found to be effective than the inner faces. So that's why that was one of the limitations were for the Bligh's theory. And also even the limitations of the intermediate sheet piles also were observed. The intermediate sheet piles, if smaller in length than the outer ones, were ineffective. So that's why, so this is also one of the observations that were made. So the undermining of the floor started from the tail end. So if the hydraulic gradient at the exit is more than the critical gradient for a particular soil, then the particles would move with the flow of water, thus causing a progressive degradation of the subsoil, resulting in the cavities and ultimate failure. So that piping occurs. So therefore, it was absolute essential to have a very deep vertical cutoff at the downstream end to prevent undermining. So therefore, Khosla and his associates analyzed the composite floor and obtained expressions for uplift pressure distributions along the floor and the pile. So here the method of independent variables is discussed, where a composite weir or a barrage is split up into number of simple standard forms for which the mathematical solutions were obtained. So the standard forms can be like a straight horizontal floor of negligible thickness with pile either at the upstream end or at the downstream end. You can have a straight horizontal floor of negligible thickness with pile at some intermediate point, and then you have a straight horizontal floor depressed below the bed but with no vertical cutoff. So these were some of the standard forms that were discussed, and the Khosla's curves were developed for which we can use it in the problems. So these were some of the cases where the horizontal floor with a downstream cutoff, with an upstream cutoff, with an intermediate, with intermediate piles, or maybe a depressed floor. So these were some of the standard forms that were taken, and the curves were developed for these cases. So therefore, the plate 1 gives the values of pressures at some key points, like as I shown, like C, D, E. That is the adjacent to the cutoff at sheet piles, and just at the end of the sheet piles, like C, D, E. And then for the case of floor pile at some intermediate points, that these were the key points of the intermediate pile. And similarly, the plate 2 gives the pressures at key points and the value of exit gradients when the pile is at the downstream floor. So like this, these key points, the pressures at the key points were analyzed by using these curves, and at other points it is assumed to vary linearly without appreciable error. So how to read the graphs and all is explained in the figure itself, and when we refer the graphs or the curves, we can find out the pressures at the key points. So let us take an example of an horizontal floor of length 20 meters and pile length 4 meters, which is provided at the downstream end. So now you can see this is the graph where we have the pile at the downstream end, and for depth D. So now you know that so D is the depth of the pile, B is the floor length, which is 20 meters. So therefore 1 by alpha is nothing but D by B, which is 4 divided by 20, is 0.2. So now you can read the curves for the for 1 by alpha 0.2. So for 0.2 like this, so you can read like here this is 5D, and then you can go 5E can be read. So that is how 5E is 40, whereas this is 0.2. So then this comes to about 27%. So like this, we can read the values from the graph for 1 by alpha 0.2. Now, if the pile is provided at the upstream end, the pressures at the key points, for example, here, so this is the upstream end. So key points is C1, this is C1, and this is D1, can be. So now for this value 0.2, we have already read this 5D and 5E. So therefore, the 5C, the pressure at C1 is 100 minus 5E, which is given in the graph, which is 100 minus 40, which is 60%. So therefore 5D1, for example, here 5D1, that is below the pile, which is 100 minus 5D, which is because we have already read 27 here, so 100 minus 27, which is 73. So like this, so now the pressure here is 100%. So by the time it comes here, it will be 73%. Then by the time it comes to C1, that it will be 60%. So this is how we read the pressures from the curves. So given the horizontal floor length and also the depth of the pipe. So for example, if you take a depressed floor having a thickness of the floor is depressed by 4 meters and length is say 10 meters. So length is 10 meters and this depressed is 4 meters. So then here also, if to refer this curve, we have 1 by alpha, which is D by B, which is 4 by 10, so 0.4. Hence from the curve for the depressed floor, so we have to read this curve. So that is depressed floor. So for zero point 0.4, so 0.4 comes somewhere here. So therefore this is about 23.5 percentage. So it is given that says here in the graph, that is 5D dash, that is for the depressed curve. So 100 minus 5D dash, so that is 100 minus 23.5, 76.5 percent. So for example here Okay, so that is how we have to read from the curves. So for finding out the pressures at the key point C, D, E for the case of pile at the intermediate points, the procedure is explained in the plate itself. However, to find the phi E for any value of alpha and base ratio B1 by B, we have to read phi C for the base ratio 1 minus B1 by B for that value of alpha and subtract from 100. So like this, thus phi E for B1 by B, say for example, is zero point 0.4 and alpha is 4. Then we have to read it for 1 minus B1 by B, which is zero point 0.6 and alpha is 4. So we get from the curve as phi C is equal to 29.1. So like this, for phi E, after getting phi C value for this ratio, so it is 100 minus 29.1, which will be at the key point E, so which is 70.9 percentage. And however, for the key point D, we have to read the 5D value for the values B1 by B, which is less than 0.5. Read that value for the base ratio 1 minus B1 by B and subtract from 100. So like this, if you read for 1 minus B1 by B, which is so 1 minus zero point 0.4, which is zero point 0.6, and for alpha 4, then you can have, because you have already read this as 44.8. So 100 minus 44.8 gives 55.2 percentage. So this the procedures that has been given in this. So this is the graph where you have to read for an intermediate pile, and the procedure is given here. Okay, so that is what you should follow. So for the ratio, the b1 by b, here it is given. So if you want to read for 1 minus b1 by b, so here b1 by b is zero point 0.4, so 1 minus b1 by is 0.6. Directly you can read from this graph only. So 0.6, like this you get various the curves are there for various alpha. So phi c values can be got from here. Similarly, phi d values can be got from here. You can also find the exit gradient from this particular graph. So here it is where it is nothing but it is h by d, that is depth of the pile, into 1 by pi into root of lambda, where lambda is given by this value. Okay, where alpha is known as b by d. So here, if for example, if B is equal to 20 meters and depth of pile is 4 meters and the heading up of water is taking is 5 meters, so then alpha can be calculated first as B by D. So then that comes to 5. So from the exit gradient, say this is 10, this is 5. So from the graph, so here you can read the alpha value, which is 0.185. So one for a particular for year, for value of alpha, you can read 1 by pi root lambda, which comes to 0.1. Take this 0.185 and substitute here, so you will get the exit gradient as 0.231. So permissible exit gradients are always given. For fine sand it's 17 to 1/6, maybe coarse sand is 1/6 to 1/5, and shingle is about 1/5 to 1/4. So we can check for the exit gradients from this particular graph. So after finding out the pressures at the key points for a simple profiles, then we have to go for the correction. So the first corrections that you do is the corrections for thickness of the floor. So because whatever the pressures that the key points E and C will always pertain to the top of the floor, while actually the junction of the pile is at the bottom. Say that is E1, for example here E1, C1, and here or here like this. Okay, here. Okay, this is 100%. So we get C1, and here E1, C1, and E1. So therefore the pressures at the actual points E1s are computed by considering the linear variations between the points D and points E and C. So we can make for the corrections after we find the pressures at the key points E and C, which is actually pertaining to the top of the floor, so that can be adjusted to the bottom of the floor, where there is a junction between the sheet piles as well as the floor. And also the effect of the pile neighboring pile on the pile for which we have calculated the pressures can also be made. So for an intermediate pile, there will be influence of the outer piles, or for the outer pile there is influence of an intermediate pile like this. And these corrections is given by C equals 19 root of D by B dash into D plus capital D by D. Here B dash is nothing but the distance between the piles, and D is the length of the pile on which the effect of another pile of depth D is required to be determined. So there is an influence of intermediate pile on the outer pile of depth D, say. So the length of the pile considered is nothing but small d, and D is the depth of pile whose effect is required on the neighboring pile of depth D. So like this we can apply this formula and go for the corrections. And also because the floor was considered to be horizontal, and therefore the sloping effect was not taken into consideration. So there may be a floor, the up slope or a down slope like this in the direction of the flow. So therefore the percentage pressures may vary, which may be greater or lesser than those if you consider as a horizontal floor for the same base ratio. Hence the correction is applied as the positive for the down slopes and minus for the upslopes following the direction of the flow. So these corrections are also given in a table form for different ratios like 1:1 or 1:2, 1:3 like this. Different corrections have been given, and these corrections have to be multiplied by the proportion of horizontal length of the floor, to the distance between the two piles, okay, where this slope is there. So for example, this is BS, so BS by B dash. So if this is floor corrections we are applying to this point, so then it is, you have to multiply BS by B dash, okay. Here so the slope correction is always applicable only to that key point of the pile which is at the beginning or end of the slope. For example, this here this slope correction is not applied because this slope is not beginning of this point, whereas here we apply this correction for the point E, for a point E, okay. So this is the down slope for us, so therefore we have to apply the corrections at the point E. So different the corrections for the slope from varying from 1:1 to 1:8 has been given, varying from 11.2 to 2. So now we'll take up a problem to solve the Khosla's using Khosla's theory. Uh, for example, we have given a section of a barrage, and the various dimensions and levels are given here, and we have to find the uplift pressures at the various key points like D1, C1, E2, D2, C2, and similarly E3 and T3. And also we have to find the exit gradient at this point C3, and we have to see that whether the section provided, whatever the section that we have given, is safe against uplift, and also piping if it is founded on fine sand with a permissible gradient given as 1 in 6. So now we know this figure is given. So the total length, floor length is around 54 meters. If you add all these things, comes to 54 meters. Distance between the two piles, that is the upstream pile and the intermediate pile, is 16 meters. Whereas the distance here is so here it is just given between the intermediate pile as well as the end pile. The depth of the pile is now also varying from 105 to 97 RL. Here also 105 to 97 RL. Here 103.5 to 95. Whereas the heading up of water is 108.5 minus 105, which is 3.5 meters of water. Now to calculate the for the upstream pile, we know that the depth of the pile, the top is at 105 minus the bottom is at 97, so we have 8 meters. So here so B1 is it is at a distance 0.5 meters, so we have total floor length as 54 meters. So alpha, you know that it is B by D, so which is 54 by 8, which is 6.75. So I told you to refer the graph, we have to calculate 1 by alpha. So 1 by alpha is D by B, which comes to 0.148. Now for 1 by alpha 0.148, we know that we can pick out the value of phi D and also phi E. phi 1 is 100%. So therefore we, after finding phi d and phi e for this ratio 1 by alpha, so we get what is the pressures at the key points d1, which is at the end of the bottom of the pile, and c1 on the right side of the pile. So that gives that means from 100% it is 81%, and then goes reduced to 74 percent. So that's how you find out the pressures at the key points D1 and C1. So however, this we considering horizontal floor of negligible thickness, these pressures are determined. So therefore, we have to apply the corrections for floor thickness. So we know that the floor thickness is 105 minus 104, which is 1 meters. So therefore, since the at the bottom it is like 81%, at C1 it is 74%. It is where it is linearly applied. So therefore 81 minus 74 divided by depth of the pile into to what distance you want. If we want we want at the bottom of the floor, so it is 1 meter, so it is 0.875. So therefore in the direction of the flow, actually at the top of the floor, it is less, but at the bottom of the floor, in the direction of the flow it is more. So that's the reason why the correction is positive. So therefore 0.875 should be added to 274 to get the corrected pressure. So that is what I once again explained, that why we have to calculate what is known as 1 by alpha, which is d by b. So total 54 divided by depth of the pile, which gives 0.148. So for 0.148 you have to get the value of say phi d. So phi d is 19% and phi e is 26%. So similarly you read it for like we get 26%. So therefore so this was the upstream pile. So we get the pressure at point D1 and pressure at point C1. So the pressure at point D1 is 100 minus pi D, which is 81%, and similarly at the pressure at C1 is 100 minus phi E, which is 100 minus 26, which is 74. So that means the pressure which was at E1 is here 100%, gets reduced to 81%, and goes and again reduced to 74%. So I had already told you about the corrections for thickness, the corrections for the interference of pile number 2, that is given by this particular formula. So now the interference of this pile has to be on this pile. So therefore D is the below this level, below where we want the interference, that is 104 minus 97 is depth of the pile 2. Similarly b dash the distance between the two piles, that is 16 meters, and similarly the total floor length is 54 meters, and what the pile considered is that is pile 1, so therefore it is 104 minus 97, 7 meters. So now putting in this formula, so we get a corrections of 3.3%. So again, since it is at the rear of this okay, the point of this pile whose effect is to be determined, so therefore the correction is positive. So the heading up of water takes place, and therefore due to this, and there the pressure is built up, so therefore the pressure increases here, and that's the reason why the correction for thickness is also positive, whereas the corrections for interference is also positive. So instead of 74 it gets corrected to 78.2. so we don't apply any corrections here, so because here we have already the corrected pressure is now 81% at D1. Like this, by referring the curves for intermediate piles also we can find out. So pile number 2, so here also it remains the top is at 105, bottom is at 97, so 8 meters. So B is 54 meters. Similarly we should calculate what is the distance of the intermediate pile from the upstream end, so which comes to 16.5 meters. So for intermediate pile, so this distance is needed, so therefore alpha is B by D, so which is 6.75. we should calculate what is known as B1 by B. So that means the distance of the intermediate pile from the upstream end is 16.5. Total length is 54. That comes to 0.306. Now from the curves for alpha 6.75 and only B1 by B as 0.3, we should calculate what is known as a phi C2. That is 52%. So here the pressure at the point C2 is 52%. Now for getting the pressure at E2 and D2, we should for the value alpha and the ratio 1 minus not b1 by b, 1 minus b1 by b, so 1 minus 0.306 is 0.694. So for that we have to refer the curves, then get the values for phi c and phi d. So once you get phi c, then phi e2 is 100 minus phi c, whereas after getting phi d we get phi d2, which is at the bottom of the pile, which comes to about 100 minus 38.5 is 61.5%. So that is what is shown here. So now I have told that for the curves for alpha 6.75 and b1 by b, so you have to refer a phi c curve. So directly for the ratio 0.306 we have to get for alpha, so you just pick out the curve that is alpha here 5 6, somewhere here it comes. Okay, for alpha 6.75 we have to pick out the ratio, which comes to about 52%. Now but for referring for E2, that is here, now this pressure is here, which is 52, that is C is here. To get E and D, so we have to get for this ratio, which is 1 minus B1 by B, which is 0.694. So again refer this phi c curve and get the value, so which is 20 for 6.75, and for this ratio, which is 6.694, somewhere here it comes. So it comes to 27.5%. Therefore the pressure at point E, that is it as 100 minus 27.5, which gives 72.5%. Similarly, you have to refer this curve for the same alpha, for the value of alpha, as well as for the ratio 0.694, we get 61.5%. Now the corrections have to be applied here. The corrections for the point E2 and C2 have to be applied. Similarly, we have the corrections for phi C2, that is because the pressure, and because between the point D2 and C2 we have to get. So here pressure is 61.5, whereas the pressure is 52. So that means 61.5 minus 52 divided by the depth, that is 8 meters, into to what distance you want. So if we want at this 104 level, so it is into 1 meter, so it is 1.2%. Okay, so 1.2%. You know that as in the direction of the flow, when the pressure is going on reducing, and it will be here more. When you come up, the pressure is definitely lesser. So what you got from the graph is lesser quantity. So that's the reason why for C2 we have to have the positive, that this correction is positive. So therefore we should add 1.2 percentage to the value that you got for C2. Similarly for E2, what happens is that, so we have to interpolate between E2 and D2. So here the pressure here was 72.5, whereas the pressure here was 61.5. So interpolation is 72.5 minus 61.5 divided by 8 into 1, where at 104 level. So therefore again here, okay, here actually the point E2 from the graph, he was somewhere here at the top of the floor, which was actually more here. Okay, more here. So therefore here the pressure here will be definitely reduced here. So therefore a negative correction is applied. So therefore 1.4% is the negative correction that we apply. For C2 we have to apply positive corrections. Okay, so you have to correctly see the corrections to be applied, and also the interference for the interference of pile 1 have to be taken. So the interference of pile 1 is on only on E2, it's not on C2, whereas for interference of pile 3 is there on C2. So therefore you have to be very careful. So when we apply correction for E2, there is interference from this pile. So that is now again given as, now you know that the it is same as what we did for this pile. So because all the depth, everything remains the same. However, I have calculated 19 root of, so what is the depth of the pile? It is 7 meters. Capital D is for this, which is this 104 minus 97, which is 7. Distance between two piles is 16 meters. Capital D and small d are 7 and 7. Total is, so it is 3.3 percentage. So now since we are calculating here, and this is at the rarer one, okay, because here we are applying the interference of this pile, and this is at the back now at the front of this pile. So therefore the correction applied will be negative. Okay. So again we have to apply the corrections for the interference of pile 3. So here capital D is nothing but of the pile 3, where okay, that is where we want to apply at this level we want to. So we have to find the depth. So this capital D is always where you want to apply, from there from that level to the bottom. So that is 104 minus 95, that gives 9 meters as the capital D, and D is for the depth of this pile, which is 104 minus 97, which is 7 meters. The distance between the two piles is now known, which is 37 meters, distance between pile 2 and 3. And similarly the total length is 54 meters, so therefore we'll get. So now since we want to find the effect here C2, and this point is on the front side. Here the pile is on the front side, so heading up of water takes place, so the pressure will increase, so therefore it is positive. So therefore 2.8% is positive, that correction to be applied to point C2. So hence and also the slope is also taken here. In this case the starting of the slope is a point C2, so correction should be applied only to C2. So from the table for 4:1 we have 3.3 percentage. For the upslope we take it as negative. So horizontal length between the floors is 4 meters, whereas the horizontal length is 4, and total the total length is here, distance between the two piles is 37. So we have to apply and that means that corrections have to be multiplied by this ratio, which is horizontal length divided by the total distance between the piles, which is 0.4%, which is again negative. So 3.3 is converted, so only 0.4% is applied as the corrections. So therefore the corrected pressures at E2 will be for the thickness. So actually pressure is 72.5. We should apply for the thickness, which is 1.4, and also we have to apply for the interference of this well, which is 3.3. So that gives 67.8 percentage. Similarly at D2 it is 61.5, and C2 we have to apply for first the from the graph it is 52%. So we apply correction, which is 1.2, and then we apply corrections for the mutual interference of this pile, which is 2.8, and similarly for the slope, which is 0.4. So it comes to 55.6 percentage. Now for the downstream pile, which is pile number 3, we know that D is 103.5 minus 95, which is 8.5. So the total width is 54. So we have to refer this the curve. So there is 1 by alpha, which is D by B, which is 0.158. So directly for 0.158, read the graphs for 5D as well as for 5E. So you will get 35 and 24% respectively. So directly for these values you have to read and get the answers. Again the corrections should be applied. So corrections for thickness. So we know for applying for corrections, we know the pressures at D3 and E3, and so that gives the corrections for thickness, which is 35. Here it is 35 and here it is 24. So 35 minus 24 divided by depth of file 8.5 into distance. Here we have 103.5 minus 102. So that gives corrections as 1.9%, which is negative. So as the flow takes place, here it goes on reducing, then again goes on reducing like this. So reducing, and then okay, here at this point, okay, so is it not? So that's why the corrections here is the correction 1.9. So actually you will get slightly more, but actually it is slightly lesser, so therefore a negative correction is applied for the thickness. So as we come from top, because by referring we have measured at the top, which is actually slightly more. When you come down the pressure reduces, so that's the reason why a negative correction is applied. Also interference of this pile has to be done. So here we have to be very careful. So depth of the interfering pile has to be taken from the RL 102. So 102 minus 97 gives 5 meters for the pile 2, whereas for pile 3 it is 102 minus 95, which is 7. So total distance is 37 meters, so therefore we get a correction which is 1.55. So here we can note that it is here the interference of this pile is taken here, okay, and this point is E3 point is in front of this, so that's the reason why a negative correction is applied. So therefore the corrected pressure is 35, what we got from the graphs. So we applied for the thickness, correction for thickness as well as for the interference, but no corrections applied for the slope, because E3 is neither the end point of the slope nor the starting point of the slope. So that's the reason why the correction for the slope is nil. Now the various percentage pressures and the actual pressure heads at the key points are written, which we have founded after giving the corrections. These are the values that we determined at each of the key points, D1, C1, E2, D2, C2, E3 and D3. So now multiplying by the total head, that is 5 meters, we have so 5 into 0.81 gives 4.05, multiplying by 9.81 gives so much uplift pressure. Similarly, it's a 0.782 into 5 meters gives 3.91, multiplying by 9.81 will give 38.3, so on we can calculate. So for 24.24 into 5 gives 1.2, multiply by 9.81 gives 11.77 kilonewton per meter square. Now we have we can find out we can check the thickness of the floor. To check the thickness at the key points like A, B, C, that we can find out the pressure head at each of the points at A, B and C. So however we have the pressure heads we can linearly interpolate here by referring the figures. So the pressure head at A, B and C is determined by interpolation. So two specific points are given here, which is so the pressure at upstream end is 2.6, whereas the downstream end is a 1.58. In between we want for 7 meters, what is the distance between the two piles is 37, so that the 2 points is 37, so therefore we are interpolating and getting the answers like 2.41. Similarly at B point also, which is at a distance 24.5, where the pressure is pressure head is 2.6, so that is the here then the end point is 1.58. So intermediate point, that means at each of the end, so at starting point of 37 is 2.6, the end point is 1.58, like this. So in between this is at a distance of 24.5 what we want, so that's why by interpolation we got 1.925. Similarly we have at a distance of 30.5, which is the point C, from the starting of the pile, intermediate pile, so therefore the by interpolation we got 1.76. so taking specificity G as 2.4, we can find thickness required, so which is given by, so 2.41 divided by G minus 1. You can multiply by 4 by 3, it is not required because actual pressures are calculated here, and that's why that variations is not accounted. However, so 1.72, but we have actually provided 2 meters. Similarly at B, the pressure is 1.925, so divided by 1.4 we get 1.375, we have provided 2 meters. Similarly the thickness that is provided is 1 that is 1.26, what we have calculated, 1.76 divided by 1.4, so therefore the provided is 1.5 meters. So hence the thicknesses whichever are provided is safe. So to calculate the exit gradient, we have the seepage head. So seepage head is 108, so top level water level, and no water on the downstream side. So 108.5 minus 103.5, which is 5 meters. So depth of downstream cutoff is given, which is D, which is 8.5 meters. We should calculate what is alpha. So alpha is now B by D, so 54 divided by 8.5. So now for the value of this alpha, we should directly read from the graph 1 by pi root lambda, which is 0.16. So now you can substitute in this formula, get the exit gradient is 1 in 10. So but the permissible gradient is 1 in 6, hence it is safe. So that is what this is the graph that is to be applied. So we for alpha 6 somewhere here, so we can read the graph which comes to about 0.165. So therefore substitute the value of 0.165 here. H is known, D is depth of the cutoff, so it is 1:10. So that is the problem which was covered in detail. So how to calculate the pressures at the key points, and how to calculate the thicknesses and see whether they are safe, and how to apply the corrections. Okay, so these were some of the things that were discussed in the first problem. These very simple problems where we are required to just to refer the graphs and get the pressures at the point EDC, E1 and D1, also to get the. So we know that the pile 1, so D is 6 meters, B is 24 meters. So similarly B1 is 4 meters. The distance of that pile is 4 meters. So the alpha is B by D. So 24 by 6, that is 4. So B1 by B we can calculate 0.16. Now for value for the pressures, the point C, that is okay, you can get for alpha 4 and B1 by B. So we can get from the graph, okay, so which is 52%. Similarly for alpha 4 and 1 minus b1 by b, so then you can refer by the phi c and phi d values and then get the pressures at the point E, which is comes to 82%, because we are reading this value which is 18, and similarly we are reading this phi d value, so which gives the pressure at the key point D, so which is 66%. Similarly, for the downstream pile, we can know the depth of the pile, and similarly B is 24 meters. So 1 by alpha is that is D by B, which comes to 0.33. Directly read for 0.33. So you will get the pressures at the point E1 and D1. Similarly, exit gradient is the H is 5 meters, depth of downstream cutoff is 8, total floor length is 24. So get alpha is B by D, which is 3. So read from the exit gradient curve as 0.23 for 1 by pi root lambda. Substitute here and get the exit gradient, which is 1 is to around 7, say. So that was very simple problem where you need not apply the corrections for the thickness nor for the mutual interference of the piles. So we'll take one more problem so that you'll it is same as the first problem, so only a few data changes, but I will quickly run through this because I have explained in detail in the first problem. So there are three, again as usual there are three intermediate three piles with one intermediate, one upstream pile and the downstream pile. So total floor length as given is 57 meters, and similar distance between the intermediate and the end pile is around 40 meters. So we have the total depth of level of water is 155, it rises to 155, and here at the downstream side is 152, so it is about 3 meters of water. Okay, the seepage head is around 3 meters. 155 minus 152. Now, for the upstream pile, we know that the total floor length is 57. Depth of the pile is 6 meters. So 154 is the top of this. Bottom is at 148. So 6 alpha is B by D. 57 by 6. That's 9.5. So we have to read for 1 by alpha. So for 1 by alpha 0.10. So we get directly the value for the, if you refer phi D curve, so 20%. If you refer phi E curve, we get 29%. So therefore, the point C1 we get 100 minus phi E, which is 71%. Similarly for D1, at the bottom of the pile we'll get 100 minus phi D, which is 80%. So that means from 100% it goes to 80% and then reduces to 71%. Here the corrections should be applied. The corrections for the floor thickness has to be applied. So because the pressures that we get is at the top of the floor, so for 1 meter we have to give the corrections. We know the pressures which is 80 and 71. At the bottom it is 80 and the top it is 71. So 80 minus 71 to total depth is 6 meters into 1. So that is how we get 1.5%, which is the positive corrections that you applied. So similarly, the corrections for the interference of the pile 2 can be applied. So now so D is the pile 2 depth, which is 153 minus 148, because we are applying the corrections 153 level. So it is not 154 minus 148, it is 153 minus 148, which is the depth of the pile, and therefore distance between the piles 1 and 2 is 15.8, and similarly the total floor length is 57, and depth of the pile 1 where we have to find the effect is 153 minus 148, which is 5. Therefore apply the correction. So since it is at the pile is here, the intermediate pile has the effect on this, so it is at the back side heading up, the water takes place, pressures will be more, so therefore it has to be 1.88. so that means this correction 1.88 is positive. Similarly, there is no slope at the starting point of C1, hence therefore the correction to slope is 0. So now the corrected pressure here, E1 we don't apply, D1 we don't apply, only the correction due to the, that is, thickness of the floor is 1.5, and due to interference is, so that's why it is 74.38. Similarly, for the intermediate pile, we have the depth of the pile as 6 meters and the floor length is 57 meters. And from what distance from the upstream end is the pile 2, that is at 16.4 meters. So 16.4. So alpha we have to calculate B1 by B. So now we have to refer the curve, which is the second set of curves. So where alpha is 9.5, for B1 by B ratio only you have to get directly the value of 5C2. So that means at point C2, so that is at the right side of the pile of intermediate pile, which is 56%. But to get the left side of the pile, that is E2 and D2, we have to refer for the ratio 1 minus B1 by B. So for referring 1 minus B1, that is 0.71, for alpha 9.5, we get these values. So therefore point E2 will be 100 minus 30, which is 70%, and for D2 it is 37%, we have got from the graph. So 100 minus 37 is 63. So like this, so now at E2 it is 70%, gets reduced to 63%, and then get reduced to 56% at C2. So what are the corrections that you apply for point E2, which is on the left side of the pile? So floor thickness have to apply. So because the pressures are got at the top of the floor, for 1 meter we have to give the corrections. So it is varying between 70 and 63. Okay, so at E2 it is 70%, at D2 it is 63%. So 70 minus 63 over the depth of the pile into what distance you want. So 1.17%. Actually the pressure that you got is slightly more, so therefore the pressure will reduce, so therefore you have to apply negative corrections. Similarly, the corrections for the interference of pile 1 has to be not pile 3, so therefore the depth will be 5 meters. Similarly for the pile 1, where the effect has to be taken into account, and D is the depth of the pile that is considered, which is 5 meters. So distance between the two is 15.8, so therefore the correction is applied. Since the point E2 is in the front side, so therefore it is the negative. Okay, negative corrections to be applied. So correction due to slope is nil again. So now for E2 we have to apply the corrections. It is 70 for floor thickness, it has to be deducted. Again for the interference it has to be deducted, which is 66.95. Similarly for the right side of the pile or intermediate pile, for C2 we have to apply the corrections. So again the corrections actually at the top of the floor, here where because in the direction here this so where the for because it is got at the top of the floor, we should always calculate at the bottom of the floor. Actually the pressure that what you got is slightly lesser, so therefore we have to get more pressure because in the direction of the flow. So where we have now 1.17%, that what you got we should be added to get the correct pressure at C2. Similarly, the interference of pile 3 has to be calculated. So where we have, so what is the depth of that pile 3 at the from the level 153 has to be calculated. So 153 minus 141.7, which is 11.3 meters. Similar depth of the pile considered is pile 2, which is 5 meters. The total distance is 40 meters between the two piles and B. So here the correction should be applied. So here it is the E2 is rear of the pile 3. So heading up of water takes place, pressure increases, so 2.89 has to be the positive correction to be applied. but the correction for the slope is also, since there is a slope there, since it is an upslope, correction is negative. So slope 3:1 is given, so therefore the correction is 4.5 percentage. So the actual correction should be multiplied, because that correction should be multiplied by the horizontal length of the slope, divided by the distance, so that gives 0.34 percentage. So therefore the corrected phi C2 gives us 56 plus 1.17 plus 2.89 for the mutual interference, and minus 0.34 is for the slope, so which comes as 59.72. So therefore from E2 it is 66.9, goes down to D2 which is 63%, and then comes up to C2 which is 59.2 percentage. So that's how the pressure goes on varying. Now for the pile 3, so the depth of the pile is from, that is the top level is 152, bottom is 141.7, that gives 10.3 meters. So distance, total horizontal length is 57. So for 1 by alpha we should calculate 0.18. Then directly from the graphs you can read and get for E3, that is 38%, and D3 is 24%. So the correction should be applied only for E3 for a correction for the thicknesses. So therefore the correction for thickness comes to, so because that for depth, for thickness of the floor of 1.3 meters we have to do the corrections. At point E2 it is 30, point E3 it is 38, and point D3, okay, D3 it is 32. So over the interpolation is done, and for 1.3 meters, so 0.76, and this is actually negative. Okay, so as it comes down, so the direction of the flow, so the pressure that is measured from the Khosla curve is slightly more, and therefore we apply the corrections negative. Similarly, the corrections for interference of pile 2, that is intermediate pile, has to be calculated. From the depth 150.7, how much is the depth of that pile is to be known, 148. So that is 150.7 minus 148 is 2.7 meters, which is pile 2. And similarly, the depth of the pile 3 is 9 meters. Total distance between the pile is 37, so therefore B is 57. So therefore we get the correction as, so 19 into root of 2.7 into 37, so this is, it comes to about 1.05%, okay, which is a negative. So here the correction to the slope is nil, because this is neither the starting point nor the end point. So we can apply the value of that is the, we can correct the pressures at the point E3, that is the 38 minus 0.76 for the thickness, and for the interference it is 1.05, so that gives 36.2 percentage. So like this we can